Alrighty. So today we're just gonna be talking about glycogen. So this is my YouTube channel. I'm gonna be posting content about my test that I'm studying for called the CBSE for the oral surgery exam for any family or friends that are watching. A quick explanation: the CBSE is a exam specifically made for medical students to prepare to take the step one board exam in their second year of medical school. And it's the same exact exam used for dental students who want to do oral surgery. So it involves a lot of medicine and pathways and a lot of diagnoses that may differ from traditional like dentistry. So that's what makes it fun. It makes it interesting. Um, and so yeah, I get to self teach myself 2 years of medical school, which I'm excited about. So let's get going. So today we're going to be talking about glycogen. What is glycogen? For those who know a lot about the body, probably are aware of what glycogen is, but it's the storage version of carbohydrates that our body uses. So when we eat carbohydrates or sugars, oftentimes they come in forms of galactose, glucose, and fructose are the three most common digested carbohydrates. And each of those names are a specific type of molecule. Glucose will go through something called glycolysis, which is what produces energy for our cells. So that's on a cellular basis. So we consume food, it gets digested in our intestinal, our GI tract, and then each individual glucose molecule is sent throughout the body by our bloodstream to be processed and used in each individual cell. If there's leftovers, we can then keep it in our livers and in our muscle tissue. That's where glycogen is. So what happens is it takes the glucose molecules in your blood and it will chain them up um, into it's just a chain of molecules. And I kind of drew right here. That's just kind of an example of just like a couple hexagons connected. But the point is that these molecular structures get chained up and changed in a way where they're not singular anymore, where they can be stored in like packets almost, if that makes sense. So right here, I kind of have the beginning of the process called glycolysis, which is the creation of energy. And it'll start from glucose and go to something called pyruvate later on, produce energy. What happens when you're trying, so when you eat a lot of food and you're in something called the fed state, your body's saying, hey, our cells have plenty of energy. We don't need to use any more of the glucose in the bloodstream from all the bread I ate, right? So what's going to happen is in your muscle and in your liver, it's going to make glycogen. Something to specify: why does our liver store glycogen? Our liver is kind of the mediator of our blood sugar level. So how much energy is being released or produced? And so when we fast without our liver, we would just die, right? Because we would have no backup for energy if we weren't able to eat for 24 hours. But because of human evolution and the fact that we don't eat all the time at a consistent rate, the liver is what maintains a healthy blood sugar level and releases glycogen when we're in something called a starving state, and then stores glycogen or the glucose when we're in a fed state. So we're basically just storing for a time in need when we're going to be hungry again. Okay. So, and then it'll release it. So we're going to go through the process of storage and release. So what happens is glucose comes in contact with our first enzyme called glucose 6 phosphatase or hexokinase, which will produce glucose 6 phosphate. Glucose 6 phosphate is the first step. It's an irreversible step in our pathway here. So now it can't go back to glucose, okay? So glucose 6 phosphate will then come in contact with an enzyme called, we'll pretend this is in the liver, phosphoglucomutase. Phosphoglucomutase will then turn glucose 6 phosphate into glucose 1 phosphate. A mutase is an enzyme that it basically moves a group somewhere else on the molecule. So you got to think about the glucose as one of these hexagons being a molecule. The mutase, the enzyme, takes this phosphate group, which is another chemical structure, and moves it from the sixth carbon to the first carbon. There's some biochemistry knowledge if you don't know anything about biochemistry. I hope that makes sense. So the phosphoglucomutase takes the phosphate from the sixth carbon, moves to the first carbon, and then UDP glucose, another enzyme. Sorry, UDP glucose is produced by an enzyme known as phosphoglucophosphorylase. UDP glucose is kind of the beginning of the storage. And then our famous glycogen synthase, which is the main guy, starts to take these changed glucose molecules and attach them one onto another, creating a chain that's known as linear glycogen. Now, linear glycogen is not how glycogen is stored. Glycogen kind of looks like a branch. So if you had kind of your main stem here and then branches off, right? That's called branched glycogen. And so it's making the main kind of first line. That's what linear glycogen is. Then our branching enzyme, I mean, it's in the name, right? What is a branching enzyme going to do? It's going to produce the branches. And our branching enzyme is going to produce our branched glycogen, which is our final product. That is producing glycogen. So that's in the fed state. We eat a lot of food. We go out to a nice restaurant, have a big carb pasta. Our body says, okay, cells are full. Now we're going to store some glycogen for future use. Okay, so now let's say we've been fasting for 24 hours. Our body has no more digestible food in our GI tract. It's now completely relying on our liver and the glycogen in our muscle tissue to survive. So this is where branch glycogen will go up through a process called glycogenolysis, right? Glycogenolysis in Latin, genolysis is the breakdown, so the breakdown of glycogen, right? And then the process of forming glycogen, I don't think I said that. That's called that is called, I'm brain farting on the word, but I'll come back to it. So glycogenolysis first starts with a step used known as glycogen phosphorylase. That's the enzyme. Glycogen phosphorylase produces something called limit dextrin. So it's basically just slightly modifying the branched glycogen by removing all the branches. Okay. So this glycogen phosphorylase, it's removing all the branches, breaking down the branches to produce limit dextrin. The thing is, with this glycogen phosphorylase, it can only remove the branches up until there's 4 carbons left. So you can pretend that this guy right here are 4 carbon chains popping off the main branch. So it can only get that far due to the intermolecular qualities and characteristics of the glycogen branches. So its enzyme doesn't have the capability to go any further. So it leaves these 4 carbon branches. So what happens is something called 4 alpha D glucotransferase, right? Transfer, right? Out 4 alpha D glucotransferase comes in and it removes these 4 carbon branches here and sticks them onto the end, creating basically a completely linear dextrin. And that's called a modified limit dextrin. The modified limit dextrin now can have alpha 1,6 glucosidase come in, rip them all off, break them into pieces, and send the individual glucose molecules back into the bloodstream. Right. So remember that we are turning glucose, right, into glycogen and glycogen back into glucose. So it's a reversible and irreversible process. But through the irreversible processes, we need enzymes, right? So a reversible reaction means it can happen on its own, but if it needs an enzyme, that's an irreversible reaction. So this step 1 was irreversible, but because we have the glucose 6 phosphatase, we can turn glucose 6 phosphate into glucose super easily. Okay, we'll keep going. I don't know why I got scared in front of the camera, but the production of glycogen is called glycogenesis, and then the breakdown of glycogen is called glycogenolysis. I don't know why I brain farted that. But let's talk about hormone used to determine and predict and kind of like regulate the release or buildup of glycogen. So this is how your body knows, your liver knows it's in a fed state or a starving state. So your brain is constantly monitoring along with other organs, your blood sugar levels. And so it's going to release these hormones and tell your liver what to do. So it's kind of like the command center, right? It's like a message. All hormones, if you don't know a lot about physiology or pathology or, whatever, all hormones are really just ways to send messages, to do things. Okay. So there's three main big hormones that we're going to be talking today: glucagon, epinephrine, insulin. Okay. So glucagon is released when you're starving. Okay. That's the job of glucagon. So it's going to release when you're starving, and it's going to tell your liver to release glycogen, right? Because we're hungry, we want glycogen. Insulin is released when we are full, right? Insulin is saying, hey, I've got a lot of digested sugar in the blood and we need to do something with this. So insulin will bring the sugar from the blood into the cell. So it's kind of like the bridge, right? So full, starving. Epinephrine. I love to talk about epinephrine like it's like when you see a bear. So epinephrine is just like you see a bear. Like your sympathetic nervous system is stimulated, you respond, your heart rate goes up, your eyes dilate, and it tells your body to release glycogen. Because if you see a bear, what are you going to need to run from it? A lot of energy, right? So epinephrine controls our sympathetic response, which is going to have, our sympathetic response releases the epinephrine, which then is going to cause glycogen to be released to produce glucose to go into your bloodstream and increase your blood sugar levels. So your cells have more access to more product to produce that ATP or energy. ATP is the unit of energy in our body. So we're trying to make it, right, to do stuff with it. Okay, like move our muscles. Okay, and run away from the bear. So glucagon binds, and it's going to just be a classic binding to the outside of the cell wall, which will cause the release of something called a beta subunit, which is kind of a general term for a secondary messenger in the inside of the cell. So here's the inside of the cell, outside of the cell. Glucagon binds to receptor, releases a beta subunit, which then activates something called adenylate cyclase. This is a really common pathway in a lot of different type of hormonal receptor pathways. Uh, Adenylate cyclase takes CAMP, which is cyclic AMP, and turns it and phosphorylates it to become PKA, which is just a changed version of CAMP. So adenylate cyclase grabs a bunch of CAMP, turns into PKA. That's really it. PK will travel down, and PK will upregulate the glycogen phosphorylase. So if you go back to our system here, what does glycogen phosphorylase do? Oh, it starts glycogenolysis, the breakdown of glycogen. So glucagon upregulates PKA, which upregulates glycogen phosphorylase, which produces more glucose, releasing glycogen into glucose. Okay, epinephrine. Remember, we see a bear, what do we want? Energy, right? So our epinephrine is going to bind to our beta epi receptor, which is going to produce two different types of mechanisms or pathways based off of whether we're talking about the liver or the muscle. Remember, there's liver cells and there's muscle cells. Both of them deal with glycogen. If you are in the muscle cells, you'll just have a beta epinephrine receptor, which releases a secondary beta subunit and will cause CAM to turn PK. Same exact system as we talked previously. I don't know if you can see that super well. Maybe we can like get this really close here. I hope you can read my bad handwriting. Okay. So I was talking about this, right? So it's going to upregulate. Now you're going to have glucagon and epinephrine creating the same pathway, upregulating glycogen phosphorylase. Why would we want that? We see a bear, we're scared, we're starving. Or we're scared from the bear, we want energy, right? Okay. If you're a liver cell, right, you can use an alpha epi receptor pathway, which activates in a pathway called the IP3 DAG pathway, which then will go to your ER, which stands for your endoplasmic reticulum, which is what stores and packages stuff. And it has a lot. It will release calcium and something called calmodulin. Calmodulin and calcium are stimulants. for this pathway, and so it's going to now upregulate. So if there's more calcium, it's going to bind to glycogen phosphorylase and upregulate it as well. So you can now have two different pathways, whether it be the beta epinephrine receptor pathway, which we talked about releases the beta subunit, produces CAMP, PKA, PK upregulate stuff. And then, or you could have the calcium. So you have two different pathways, double the power, right? And then insulin, which is the opposite of what epinephrine and glucagon does, which releases glycogen, or glycogenolysis, right? Now we're talking about glycogenesis, the production of glycogen. Genesis, creation, right, in Latin. Okay, so insulin, it'll release CAMP, and then CAMP will go directly to glycogen synthase, which if you look at our sheet up above, do you see this? Glycogen synthase produces linear glycogen. So if it's upregulating glycogen synthase, it's now going to try to make more glycogen. But the other really important thing it does, it produces, CAMP will upregulate the production of protein phosphatase, and protein phosphatase downregulates glycogen phosphorylase. And glycogen phosphorylase, if you remember, is what breaks down glycogen. So it's down regulating the stuff that breaks down and up regulating the enzyme that produces glycogen, making more glycogen. So insulin, you just ate a big meal, got to bring that, got to get the sugar out of the blood. Kind of fun side note, type 2 diabetes, type 1 diabetes, right? What are they, right? It's uncontrolled high blood sugar levels for an extended period of time, and that can cause a wide variety of issues. Why? Well, chemically, sugars, specifically reducing sugars, are somewhat unstable molecules that can rip protons off other things and cause all types of havoc. And so that's why you see all these issues in type 2, specifically type 2 diabetics, which has more uncontrolled blood sugar levels based off of both genetic and dietary factors. Type 1 diabetes is different. It's an autoimmune disease. But that's what's interesting is this is what's dictating where your blood sugar level should be. Because if it's too high, you're going to have serious damage to your body because of the sugar being a reducing sugar, causing all types of issues, and doing something called cross-linking. And then if it's too low, you faint and your body shuts down because it has no energy. So, this is life or death, right? So speaking about life or death, we're going to talk about a lot of diseases right now that impact this pathway. So I just took all this time to explain the pathway. So when I talk about the diseases that impact this pathway, it'll make more sense. So all these enzymes I talked about, glycogen synthesis, glycogen phosphorylase, right? Alpha-1,6 glucosidase. These are all necessary to live. What happens if you have a genetic condition that when creating these enzymes, it doesn't make the enzymes, right? It stops producing said enzymes. What do we do in those cases, right? And that's what these are. These are all basically just genetic conditions where the enzyme that we need to create this pathway isn't being produced because of some type of miscode in the protein creating process. Okay, so number one is called Van Clerk's disease. Van Clerk's disease is where our glucose 6 phosphatase is not being produced, right? So that specific enzyme is not being produced, meaning we cannot turn glucose 6 phosphate into glucose. So what does that mean? We're going to have a lot of glucose 6 phosphate. We're going to have a lot of things stuck right here where this one is. Okay, so what does that mean? So if that is the case, you're going to have a lot of problems, right, in both your liver and in your muscle tissue because this enzyme impacts both, right? So you're going to have stuff like hepatomegaly, which is swelling of the liver, splenomegaly, swelling of the spleen. You're going to have hypoglycemia. Why would you have hypoglycemia? Hypoglycemia is a condition where you don't have, it's a state where you don't have a lot of glucose. Why? Because you can't make energy with glucose 6 phosphate and you can't put this in the blood yet. You can only put glucose in the blood. So you got a bunch of stuff that you can't send out. So you're going to be hypoglycemic because you don't have any glucose because you're not getting it to glucose. It's just sitting right there as glucose 6 phosphate. You're going to have ketoacidosis, which is the production of ketones, which our body does when we're starving, which makes a lot of sense. And we're going to have an increase in triglyceride use, right? So if we can't produce glucose, what are we going to lean on? We're going to lean on ketones and fats, right, to fuel our body. The one specific thing about Van Clerk's disease is that it has super high lactic acid production because your body still has lots of pyruvate. Notice how we can't go up to glucose, but what can we go down to? Pyruvate. Pyruvate, what does that do? Pyruvate can go, down in the electron transport chain and do all types of stuff, right? But our body, because there's so much glucose 6 phosphate, it's going to produce a lot of pyruvate, and it's going to go down to the ETC, the electron transport chain, right? And this is going to be really upregulated, and this can only be used for so long, or it can only be so full. It's kind of like a ball pit, right? I don't know if you like saw those ball pits as kids, but there's someone else on the windows kind of creeping me out. Okay, so a ball pit, right? And you can only put so many balls in that ball pit. That's how the electron transport chain is. It produces a lot of energy. It's super efficient, but it's a ball pit. So what happens when you make exponential glucose 6 phosphate because it's not going up to glucose? So then you push down to pyruvate, and now all this pyruvate is just shoving into the Krebs cycle and eventually electron transport chain. Um, what do we do in that case? So we shift to the left here and go where we don't need this cycle, which is producing lactate, which produces energy and creating eventually lactic acid. So lactic acid, the lactate push, we hear a lot when we're like exercising. It's the anaerobic form of producing energy that our body uses. Anaerobic meaning without oxygen, right? So if we don't have access to oxygen, which the electron transport chain needs, we go that way. In this case, we do have oxygen, but the ball pit's full. So we got to go through the anaerobic process and produce lactic acid, which can send our body into metabolic acidosis, which means there's so much lactic acid in our body, our entire body becomes more acidic, which is bad. That will kill you. Okay, so something that we can test for, these diseases are called GCDs, right? Glycogen synthesis diseases. Is that right? GDS. It's glycogen synthesis disorders. So GCDs. So that's the first GCD. What we can test for all of these is something called a periodic acid shift test. And what it does is it tests positive for an excess amount of glycogen, basically. So you can test in your liver cell. You can take a sample of cells and test for, one of these disorders based off of how much glycogen is there, right? So it's going to come up positive for the periodic acid shift test. All of them are. So that's kind of like your base level. So this doesn't tell you the PAS is what a lot of people call it. A PAS doesn't really tell you which GSD, glycogen synthesis disorder, it is, but it will tell you that it's one of them. So if you're working in a hospital system or a patient comes in with all these problems, this narrows your scope to like 7 diseases, which is super nice. Okay, so your supplement is cornstarch. Cornstarch is a super quickly and easily digestible glucose. So you're hypoglycemic, you don't have any glucose, get some glucose in the dude, and they're gonna feel better. Okay. And then long term, there's nothing really to do. There's no enzyme therapy. It's really just continuing to monitoring your blood sugar and consume cornstarch or other fast sugars. Okay. So like I have here, this is going to be experienced in the muscles and the liver. So some of the symptoms that you're going to feel are going to be both in the muscles and the liver. Okay, Pompe disease. So number 2. I got to go faster here. Pompe disease has to do with this really cool enzyme called alpha-1,4-glucosidase. Remember we saw this alpha 1,6. Alpha and the 1,6 just refer to specific bonds in glycogen, if you don't know. So alpha 1,4 glucositis only impacts lysosomes. Lysosomes are important part inside of cells, and those will only be found in muscle cells. So this is impacting lysosomes, which are only in the muscles. So I have muscles only here, and over here I have kind of each of the chromosomes section of an allele that like codes for these enzymes, but I don't really want to talk about that. Okay, let me get a drink of water. Let's keep cooking. So, Pompe disease. So you're going to experience a lot of muscular issues rather than liver issues. Okay. So the big thing with Pompe disease, the screams Pompe disease, is heart problems. Your heart is made up of a lot of muscle. And specifically, you're going to first experience symptoms in your quads, your quadratus femoris, the big muscle in the front, because that's your biggest muscle. So muscle fatigue is going to come from your biggest muscle first. And you're going to basically start with the quads, and it's going to make your way to the heart. And eventually you're going to have seriously gnarly heart conditions like hypotonic cardiomyopathy, which is just failure, growing, and swelling of the heart, and conduction blocks, meaning that your conductive circuit that's contracting your heart to beat isn't working as well anymore. And that's because your lysosomes aren't working. And if your lysosomes aren't working, your whole cell stops to work. So then cells are dying in your heart, and then other cells are trying to make up for the dying cells in your heart, causing your heart to swell, causing myopathy, causing all types of problems. Okay. A hypertrophic, your heart becomes a term called hypertrophic, which means it swells. Okay. There is enzyme replacement therapy, so you can replace this enzyme. So muscle only, but specifically in the worst conditions, it will be impacting the heart. And that's what we're concerned about. If your heart stops, you die. Okay. Step 3, we're going to talk about this enzyme right here. So that second enzyme was glycogenolysis, is the breakdown of glycogen. I didn't really explain this well. I'm sorry. In lysosomes, you can turn branched glycogen into glucose in one step. Instead of doing this whole process the rest of our body does, they get to just do in one step. I don't know why, but they get to. So this one enzyme that can turn branched glycogen, the final form of glycogen, just back to glucose, that's only in lysosomes. The rest of the body has to go through glycogenesis and glycogenolysis in this very specific way. Okay. So step 1 was the last step of Van Clerk's disease is all about the last step of glycogenolysis because it's turning glucose 6 phosphatase into glucose. Okay, 3 is also about glycogenolysis, Cory's disease. It's where we're deficient in 4-alpha D-glucotransferase. Why is that important? We can't turn limit dextrin into modified dextrin, meaning we're not breaking down the branches, meaning our alpha 1,6 glucosidase can't ever get to it, and our glucose 6 phosphatase can't ever get to it, okay? So that's a problem. So what we're going to see here is we're going to see similar presentations to Van Clerk's disease, right? Because now we're impacting both muscle and liver. We're going to be hypoglycemic because we cannot produce glucose, right? We don't have any glucose in our system. The only difference with this one is that there is no buildup of glucose 6 phosphate. Remember how I talked about the whole ordeal about glucose 6 phosphate, where it goes, the buildup of pyruvate, lactic acid, and all that jazz. There's no lactic acid in this case, right? Similar symptoms because they're both hypoglycemic and they're both going to rely on ketones and liver and fats to survive, right? Because you don't have any glucose, right? But the glucose gets stopped at different points. The glucose here gets stopped for Van Clerk's disease. It gets stopped at glucose 6 phosphate, but for this one, for Cory's disease, it gets stopped at the limit dextrin, the modified limit dextrin cycle. Okay, so there's that. You're going to experience cirrhosis, which is different. Infants will have a failure to thrive. There'll be some hepatosplenomegaly and actually some peripheral neuropathy as well. which is just like failure of your neurons or stimulation of your neurons in your peripheria, or it's like your fingertips and your toes and stuff. But yeah, so that's Corey's. The one specific thing about Corey's is you're going to have an increase in transaminase due to damage in liver cells. So because of the buildup of limit dextrin, your liver cells are going to be more damaged than other cells, like with Van Clerk's disease. So buildup of transaminase. What are transaminase? Transaminase are the byproduct of using proteins to survive. So, yep. This specific disease uses the ischemic forearm test, which means that we're going to cut off circulation and monitor how much lactic acid is being produced when we like use our muscles here, basically. So it's trying to figure out whether or not we're actually creating lactic acid. And in this case, there will be no lactic acid, right? Because we're not relying on glucose. There is no glucose. So they're using an ischemic forearm test. And for this one, you can really just take supplements. 4, we're going to talk about that. So Anderson's disease, which has to do with the deficiency in the branching enzyme, which is not glycogenolysis, like we've been talking about a whole bunch now. It is glycogenesis, the production of glycogen. So with the branching enzyme, you're going to experience peripheral neuropathy as well. You're going to have hepatosplenomegaly, right? So this is going to impact muscle and liver again. So you're going to have symptoms in your muscles, in your neurons, and in your and swelling of the liver, right? Because your liver's not doing good. And so the main way to tell with this guy is going to be just looking for hypotonia and cardiovascular problems. So that's Anderson's. Anderson's is really hard to tell, so they don't really test on it frequently, because it's just a very broad, generalized disease that doesn't have like very specific symptoms. But the one case is that Anderson's disease does impact infants, right? So if it's a baby coming into the hospital, you can think of Anderson's disease, because some of these will onset later on in life and become more problematic as a human becomes bigger. But with Anderson's, it's pretty early on that the patient will have symptoms. So an infant, basically. Okay. So basically a baby that's like not eating, or is eating and throwing up, or is experiencing discomfort and neuropathic problems, and also just like having a lot of issues. So number 5 and number 6 both have to do with glycogen phosphorylase, which if you remember is glycogenolysis. Glycogenolysis, breakdown of glycogen. So it's the exact same enzyme, but it's whether it's the enzyme being impacted in the liver or the muscle tissue. So McCarle disease, I always remember M for muscles, right? So McCarle disease impacts glycogen phosphorylase in the muscles, not the liver. In this case, you're going to have a lot of exercise weakness problems. And the big way to know it's McCarle's disease is that they will get really tired, and then they'll have something called a second wind, and then they'll be fine in like 5 minutes, right? Once they drink some water or something. So like basically what's happening is they can't break down glycogen very well at all. So their body, which after a couple of minutes exercise, your muscle cells really start to rely on glycogen once your systolic ATP and your creatine kinase is used up. So other like quick forms of energy are gone. Now it starts to lean on the glycogen. There's no glycogen. So your muscle cells get tired and they start to experience fatigue, these patients. But when they sit, your muscle cells recover, more systolic ATP is created, your creatine kinase levels are balanced again, and blood sugar, glucose gets back to those cells via your blood. Then the muscle cells become okay again. So it's called the second wind effect. So they're going to basically exercise, get really tired and fatigued. 5 minutes later, they're fine. Okay. HERS disease, it has to do with the liver. And it's all the same stuff. that impacts the other livers, like hepatosplenomegaly, swelling of the liver. These patients can experience osteoporosis and some other stuff like that. There is no specific way to tell that it's HERS disease over the other diseases, but besides using a PAS test to figure out if it's only the liver, and then just based off of symptomatic stuff, and then checking for the enzyme. So for HERS disease, it's just supportive care, and then for McArdle's disease, you can actually do some aerobic exercise, drink lots of quick glucose like Gatorade or something like that. That's like metabolized fast, which can help get sugar to those muscle cells because they have no access to glycogen. So that's my video. Hopefully this saves, and I'm going to post it. So, yep.